Well, hello and welcome again to Math 315. This is the third recording in the last chapter, chapter 10, on topology. And we've been talking a little bit about functions, mapping sets, and finding the image of a set. And what we're going to do now is we're going to reverse the process and look at what's called the inverse image or the pre-image. And that's going to be an important idea when we come to try and making sense of what we mean ultimately by continuity, or redefining continuity without having a notion of distance. Now in mathematics we use this symbol, which we often read as F inverse, to denote the inverse of a function, assuming that it has one. And that's all very fine, but now unfortunately, which is rather confusing, but I'm afraid that's just what happens, we're going to now misuse this symbol to refer to a set called the inverse image or the pre-image of some given set under some function f that might itself not even have an inverse. Now what do I mean by all this? Well, the best way of seeing this is to have a look at some examples. So we're going to have a look at a nice simple example. Firstly, we're going to take the function f of x is 2x, which is just our straight line. There it is, passing through the origin of gradient 2. Take the function f of x is 2x, and my set A now is going to be the set 0, 2, so on the axis here. Now, as we've been doing before, we can find the image of this set A, this interval 0, 2. Well, 0 goes to 0, 2 goes to 4, and so all the points in this interval here get mapped to all the points on that interval there. So the image f of A will be the closed interval 0, 4. What I want to now do is to reverse the process, and I want to say that the pre-image or inverse image or pre-image, both mean the same thing, of the interval 0, 4. In other words, where did this interval 0, 4 come from? Well, of course, it came from the interval 0, 2 down here on the x-axis. So instead of going from here to here, we're now going backwards from here to here, and we're going to call that the pre-image. And I'm going to use this inverse notation, but I'm going to read this now as the pre-image under f of the interval 0, 4 is the interval 0, 2. The pre-image of this set is this set under this function f of x is 2x. Now in this case, this function 2x does in fact have an inverse. On the other hand, if we're going to now take another function, we're going to also look at the interval 0, 2 on the x-axis, and we're going to map all the points in this set using the function x squared. And as we've seen before, if you map all the points along here, so 0 goes to 0, 2 squared is 4, so all the points here get mapped to that interval there. Now, if we want to go backwards, we now want to say, well, if we now take this set 0, 4, and we want all the points back on the x-axis, all the points on the x-axis that map to 0, 4, well, certainly 0, 2 will be there because we just saw that. But also note that if I took any number between -2 and 0, if you square any of those numbers and go up onto the function, they're going to land on this interval as well. So -2 gets mapped to 4, 0 to 4, -1 goes to 1, and so on. So if I'm looking for all the numbers on the x-axis here that map into 0, 4, then in fact the pre-image consists of the union of the interval 0, 2 and also the interval -2 to 0. And so we write then that the pre-image of 0, 4 is the union of this interval here, union with that interval, and because they share a common point at 0, we can combine these and say it's just the interval -2 to 2. So in this context, I'm not going to say f inverse, I'm going to talk about the pre-image of f, or the inverse image if you like. but I'm not going to say f inverse here when I read this out. This is not f inverse, it's the pre-image of this set. So when you see this with a set, think of it as pre-image. Because in this example, this function y equals x squared, f of x equals x squared, doesn't have an inverse. There is no true inverse of this unless you restrict its domain. So just do an example of one of these. So we'll have a look at the example. We're going to take fx is x squared minus 1, and we're going to look at the pre-image of the interval minus 1, 1. So here's the picture, here's the solution to this. So we're looking at the graph of x, draw pictures all the time, of course. So x squared minus 1 is our parabola, pull down 2 units here. And we're looking at the interval between minus 1 and 1. We're looking at, in fact, the closed interval. So we're looking at the pre-image of the closed interval between minus 1 and 1. So we want all the numbers on the x-axis along here. So there's f, there's x. All the numbers on the x-axis that map into this bit here. Well, minus 1 is going to come from 0. If you put 0 into here, 0 squared minus 1 is minus 1. So that's going to be 0. And then all the points along here, by the way, if you look at 1 and you say, well, what maps into 1? So put x squared minus 1 equal to 1. That gives x is root 2. That's x squared is 2, so x is root 2. Or it could have come from minus root 2. So all of the numbers along here, when you map them onto the function, they're going to go to this part of the function, and that's going to describe all the real numbers in this interval. So the pre-image of this will be this interval here from 0 to root 2. But also, if you map all of the points across here onto the function, you get this part, and that corresponds to these numbers in here on the y-axis. And so the pre-image of this will be this one or this one. That is, it's the union of these two. And of course, we can combine those together and write it as minus root 2 to root 2. Now we come now to a very important connection between open sets and continuity. And again, this is best looked at by doing an example, motivated and looked at by doing an example. So I'm going to consider this split definition function. It looks like f of x is x if x is negative, so it's looking like this. If x is negative, is strictly less than 0, it's just your old friend y equals x. And if x is bigger or equal to 0, then it's x, the line x plus 1, which is just this one bumped up by 1 unit. So in particular, if x is 0, then this is going to be 1, so that will include this point here, and it's going up with the same gradient. So that's the picture of this function. Now you can see from the diagram that this function is clearly not continuous at 0. You've got a nice jump discontinuity there. It's defined at 0, its value at 0 is 1, but it's not continuous there. And I'm now going to take an interval, an open interval in fact, 0, 2, that's between 0 and 2 on the y-axis. And that's an open interval, and I'm going to ask what is its pre-image under this function. What is the pre-image under this function? So what x values give you the y values in here? Well, if you look at the picture here, if you look here and see what x values are giving you the points in here, there are none in here. There's nothing, it doesn't cut the curve here, so there are no x values giving you y values here, but the x values giving the y values here, well, 0 is included because that point is there. So when you put x as 0 in, you do get 1. So the pre-image of this one is going to be 0 all the way along to 1, but it excludes 1 because we excluded 2. So in our picture, if you look at it, the pre-image of our set B, this one, is going to be this interval down here, that is here, with it including 0 because of the 1 here, and excluding 1 because this doesn't 2 is not in the set B. Now just notice then that we started off with an open set on the y-axis. We took the pre-image and we get this set, and this is not an open set. So in this case, the inverse image of an open set under this discontinuous function, it gave us a set, but a set which is not open. Now recall then what our definition, we'll come back to this in a moment, but recall then what we said, that a function f is continuous at x is a. Our epsilon delta definition was, given epsilon bigger than naught, there is a delta so bigger than naught, so that if x minus a is less than delta, then f of x minus f of a was less than epsilon. That was our epsilon delta definition. Now we can rewrite that definition, we can rewrite this condition using our epsilon neighbourhoods. That is, I can say if x minus a in absolute value is less than delta, then that means my x lies in a delta neighbourhood of a. So it belongs to n of a delta. And I can also write this condition, f of x minus f of a less than epsilon, by saying that f of x lies in the epsilon neighbourhood of f of a. So our definition of continuity is, given epsilon bigger than naught, there is a delta, so that if x belongs to this open set, that is this open set, then f of x belongs to this open set. And that means then that this open set here, which is this one, that this is an open set, and it is in the pre-image of this set, of this epsilon neighbourhood, which is also an open set. In other words, the pre-image of an open set is an open set. Now we can do exactly the same thing with limits, but this time we need to work with a deleted neighbourhood. That is, we can say that the limit as x goes to a of f of x is L, and now that meant that given some epsilon bigger than naught, there is a delta, so that if x belongs to the deleted neighbourhood, because x is not allowed to be a, so we're not allowed to include a in this, so it's the deleted neighbourhood that I defined in the previous lecture, then f of x belongs to the deleted neighbourhood of L of epsilon, because L is the limit. We don't actually get to L, we get as close as we like. So we have to delete that one from the definition as well. Now on the other hand, so we've seen an example then of where we had a discontinuous function where the pre-image of an open set was not open. Now on the other hand, here's another example here where I've got f of x is x squared if x is less than 1. So that's our old friend y equals x squared all the way up to here. So that's this part of the curve here. And then it's y equals x if x is bigger or equal to 1. And that just goes up here. And here you can see that it's obviously continuous. If you take a limit as x goes to 1, of either of these, you do get 1. So this function now is continuous at x is 1, and hence it's continuous everywhere. And now I'm just going to pick another open set here. I'm going to pick the open set 0, 2, and I'm going to look at the pre-image of this open set. Well, I want to see what x values map to here. Well, clearly any x value in here, this is going to map up onto here, and because this is the line y equals x, if this is 2, this is 2. So the pre-image of this is going to be this interval here. That's the interval between 0 and 2. On the other hand, any number in here, the number root 2 squares to give you 2. So any number in here, when you take that up onto the function and then push that across to the y-axis, that's going to be in this interval. So the pre-image of this now is going to be the interval from -2 through to the point 2. And in fact, that's actually not, sorry, that's not quite right. It's going to be the union of root, because we're excluding 0 here. Yeah, well, sorry, we're excluding 0 in our open set. So it's going to be, it's minus root 2 up to 0, and then union root 2 up to, so 0 up to root 2. Apologies for that. So it's from minus root 2 up to 0, union 0 to root 2. Now this is also an open set because it's a union of two open sets. I'll correct this in your hard copy. So it's the union of two open sets is in fact open. So just to summarize that, we saw an example before where we had the pre-image of an open set was not open when we had a discontinuous function. And now we see that the pre-image of an open set here is still an open set in the situation where our function was continuous. So perhaps from that we feel a theorem coming on, and here's our theorem 10.2. It says if we've got a function mapping R into R is a continuous function, then the inverse image or pre-image of any open set is also open. The pre-image of an open set is an open set. Now this result is going to give us the key in the next lecture, in fact, to defining continuity in a much more general setting where we might not have any notion of distance. And such a setting we're going to call a topological space. So topological space is going to be an abstract set where we can talk about the notion of continuity in a very general way without having to talk about epsilon neighbourhoods or distances. So let me now introduce what we mean by a topological space. So topological spaces, the notion of a topological space first appeared in about 1915 in the work of a guy called Hausdorff, a German mathematician, who was trying to understand continuity in its most general form. So a topological space consists of two objects. It consists of a set X and a collection T of subsets of X. So there's two objects in a topological space. There's an underlying set X and some collection of subsets of X. And they must satisfy the following axioms. Firstly, the whole set X has to be in this collection T, and the empty set has to be in this collection T. Now we saw before that the union of open sets is an open set, and we saw that works for an arbitrary number of set of subsets of T. So our second axiom is that the union of an arbitrary number of subsets of T also belongs to T. So you can take any number of subsets in here, take their union, and it'll still stay inside this set T, this collection T. The intersection of any finite number of subsets in T also belongs to T. So you can take any finite number of subsets in this collection T, take their intersection, and that will stay inside the set T. So they are the three conditions to be a topological space. We'll do some examples in a second. The elements of T are called open sets. We've talked about open sets before in the real plane. Now we're going to say that any object in this set T, any object in T, we're just going to call that an open set. We're going to define that to be an open set. So all we're doing here is we're just making an abstraction of what we saw happening in the set of real numbers, where there the open sets were just unions of open intervals. So let's have a look at some examples. So firstly, we're going to take the set X to be our basic set is the set consisting of 0, 1 and 2. And I'm going to take the set of all subsets of X. So that means I've got X itself, which is 0, 1, 2. I've got the empty set. I've got the set containing 0, set containing 1, set containing 2, and then the three subsets that have a pair of elements in them. So 0, 1, 0, 2 and 1, 2. And this one is a topological space, because if I take the union of any collection of these, if I take the union, say, of these two, then I would get 0, 1, 2, and there it is, there's the whole one. I could take the union of these two, I get 1 and 2, and there it is, there's the set 1, 2. So you can take any union you like. You can take the intersection of any pair, so for example, if I take the intersection of these two, then I just get 2, which is there. I can take the intersection of these ones here, and that would be the set containing 1, and there it is. And if I took the intersection of, say, these two, then I get the empty set, and there it is. So this is a topological space. Back to our previous, the set of real numbers. If we take the set of real numbers and we take T to be the set of all open sets, as we've defined earlier, in R, then the pair R and T, this set of all the open sets, this is a topological space as well, because we've seen that the union of arbitrarily many open sets is open, and the intersection of any finite number of open sets is open. We can extend this to 2 dimensions, so we take X now to be the set of all points inside the unit disk. So this is an open disk. So that is its set of, so X is the set of all points in the plane where x squared plus y squared is less than 1. So that's all the points in here. We take T to be the set of all open subsets of X. That is, all these little open disks, any little open disk you can draw inside your set X. We'll take that as my set T. And then this pair will give you a topological space. Because again, the whole set is there. That's an open set. The empty set is there, you just take nothing. And if you take the union of open sets is open. And the intersection of a finite number of open sets is open. So this also gives me a topological space. Now in the next recording we're going to define what we mean by continuity now in a topological space. And we'll see some more examples of this in the tutorial.